Introduction to Orbital Mechanics and Spacecraft Attitudes for Thermal Engineers. Part 3, Perturbed Orbits. In Part 2, we focused on the two-body problem, where the orbit was unperturbed by any other forces. In this part, we'll consider the case of orbits where we account for the effects of other forces acting on the orbit, with focus on those arising from a non-spherical Earth, and we'll see how these forces give rise to some effects that can be exploited to give the desired orbit. We'll also see how these perturbations affect the thermal environment, specifically the effect on the orbit beta angle and fraction of orbit in eclipse. Numerous examples will be presented. Recall our exploration of the two-body problem began with the derivation of the governing differential equation. The equation was derived based on the assumption that only the gravity of the central body was acting. But reality is different than the ideal case, and some interesting things happen when a perturbing force is added such that the right-hand side of the equation is no longer equal to zero. We'll explore the consequences in this part. There are many forces that can perturb an orbit. A partial listing includes spherical harmonics, that is, forces that arise due to the non-spherical nature of the central body, drag, which is caused by the spacecraft passing through space that isn't a perfect vacuum, radiation pressure, which arises from the force applied as photons strike a surface, the gravitational tug of other celestial bodies such as the Moon or Jupiter, tidal forces where the gravitational pull of, say, Earth is stronger on the near side of the Moon as compared to the far side. This can result in stretching of the Moon, and mass concentrations in which local density variations in the central body exert forces on the orbiting spacecraft. This is especially important for lunar orbits. We're going to focus on only two perturbations in this lesson, both arising from the non-spherical shape of the central body. The first perturbation is the precession of the orbit's ascending node, and the second is the precession of the orbit periapsis. The rates and directions of these effects is dependent on the semi-major axis and eccentricity as well as orbit inclination. Our unperturbed two-body derivation was reflective of a perfectly spherical central body, but for a body that isn't a perfect sphere, we can express these imperfections as the summation of terms more representative of the actual gravitational potential. Each of these terms has a coefficient associated with it, and those coefficients are determined through experimental observations. It's useful to think of the terms having different dependencies. For example, terms assigned an even number coefficient are symmetric about the equator. Odd number terms are antisymmetric. There are zonal, sectorial, and tesseract harmonics. Zonal harmonics are a function of latitude only. The sectorial harmonics are a function of longitude only, whereas tesseract harmonics depend on both latitude and longitude. Earth is not a perfect sphere. The slight bulge in the equatorial region is expressed as the J2 zonal harmonic. This bulge gives rise to two of the perturbations of interest that will be our focus in this lesson. The equations quantifying the precession of the ascending node and precession of the periapsis are shown here. We'll look at the effects of each perturbation in more detail. First, let's look at the effect of Earth's oblateness on the ascending node. For orbit inclinations less than 90 degrees, the orbit ascending node, that is the point where the orbit crosses the equator going from south to north, precesses westward each orbit. We'll call this negative. For a given central body, the rate of the precession is dependent on the orbit semi-major axis, the orbit eccentricity, and the inclination angle. For inclinations greater than 90 degrees, the precession is eastward. We'll call this positive. Mission designers can use this precession to their advantage, as we shall see. Consider Sun-synchronous orbits. These orbits are useful for Earth observation because they are designed to pass over sunlit portions of the Earth as close as possible to the same local solar current. This gives the spacecraft instruments an opportunity to gaze down at Earth with consistent illumination conditions. If we want to achieve these conditions, the ascending node needs to maintain a consistent offset from the orbit's subsolar point, and this is accomplished by moving the orbit ascending node at the same rate and in the same direction as the Sun appears to move around the celestial sphere. We said previously that, on average, the Sun moves about 0.986 degrees per day, and this motion is eastward. So we seek an orbit whose ascending node angular rate matches this movement as closely as possible. Assuming a circular orbit, we see from the equation that a number of combinations of inclination and semi-major axes may be used to attain the desired magnitude. However, it is important to note that we must make the precession eastward which means that the precession must be positive. The only way to obtain that is to require our orbit inclination to be greater than 90 degrees. One such combination is to incline the orbit 98.2 degrees and place it at an altitude of about 705 kilometers. The Oblateness perturbation also causes the orbit periapsis to precess in the orbit plane at a rate given by the equation shown. We see that the precession is positive, that is, it is in the same direction as the orbiting body when the term 4 minus sine squared I is greater than 0, and negative, that is, in the direction opposite of the orbiting body when the term is less than 0. But how can the effect of this perturbation be exploited? We saw earlier that communication satellites placed into a geostationary orbit are stationary over a given point on the ground. For these to be useful, ground stations must be able to see the communication satellite, which can be a problem for ground stations at high latitudes, as a spacecraft over the equator will appear low in the sky. A satellite orbiting at a higher inclination is desired, but the problem with that is such an orbit won't allow the spacecraft to remain over the same point on the ground at all times. However, if a Molniya orbit is used, the spacecraft will appear to dwell near the same point in the sky for long periods of time. To achieve such an orbit, we need to lock the location of the orbit apoapsis and periapsis. To do this, we desire an orbit where the rate of movement of the periapsis goes to 0. For a closed orbit, we see that this happens when the 4 minus 5 sine squared I term goes to 0. This is true when the orbit inclination is 63.4 degrees. A spacecraft in a Molniya orbit spends much of its time at high altitude and at high latitude so that it appears to move slowly near apoapsis. Due to the inclination, the apoapsis stays locked into the same position over time. In addition to the specialized orbits attainable exploiting these perturbations, there are effects of interest to thermal engineers. The precession of the ascending node changes the angle at which the sunlight falls onto the orbit plane. We call this the beta angle. As the beta angle changes, an orbiting spacecraft will experience a variety of thermal environments. Additionally, beta angle is one parameter that affects the environmental heating experienced by a spacecraft. It also affects how much time a spacecraft spends in eclipse. Formally speaking, the beta angle is defined as the angle between the solar vector S and its projection onto the orbit plane. Given its importance to thermal engineers, let's see how this angle is defined so that we can have a detailed understanding of its effects. We begin by defining a coordinate system for our calculations. The celestial inertial coordinate system is convenient as it gives us a consistent system in which to perform the required vector operations necessary to define the beta angle. In this system, the xy plane lies in Earth's equatorial plane, with the x-axis pointing from the center of the Earth to the point in space where the Sun crosses the equator going from south to north. This point is called the vernal equinox. The z-axis points from the center of the Earth up through Earth's north pole. With the x and z axes fixed, the y-axis forms the right-handed system. We need a vector that tells us where the Sun is. Here, we define the solar vector S as a unit vector in the celestial inertial coordinate system that points toward the Sun. Note that the motion of the Sun is constrained to a plane tilted approximately 23.5 degrees from the equator, called the ecliptic plane. From our definition of the celestial inertial coordinate system, the path of the Sun crosses from the southern to northern hemisphere at the location of the celestial x-axis. The motion of the Sun in the ecliptic plane is governed by two parameters, the ecliptic true solar longitude, denoted as an uppercase gamma, and epsilon, the obliquity of the ecliptic. Forming the solar vector is accomplished by performing two Euler angle transformations, the first by an amount epsilon about the celestial x-axis, and the second by an amount gamma about the new z-axis. These operations are performed on a unit vector initially lined with the celestial x-axis. As we can see, the first transformation tilts the ecliptic plane to the appropriate orientation. The second transformation rotates the unit vector in the ecliptic plane by an angle that points directly to the Sun. As we learned in part 1 of this lesson, we can accomplish this transformation by multiplying two 3x3 matrices in the order the transformations are to be performed. The first matrix is an x-axis transformation, the second a z-axis transformation. The operations are performed on a unit vector initially aligned with the celestial x-axis, which is denoted in the 1, 0, 0 vector. The result of this transformation is also a unit vector, namely S. Next, in our pursuit of an expression for the beta angle, we'll need an expression that describes the orientation of the orbit. This is accomplished using the orbit normal vector, denoted as O. This unit vector points normal to the orbit plane. This transformation requires two rotations, one to orient the orbit plane in the correct inclination and the other to position the ascending node. Since we are creating a vector normal to the orbit, the transformations are performed assuming a unit vector aligned with the celestial z-axis, that is, normal to the untransformed orbit plane prior to any transformations. The first transformation is about the celestial z-axis by an amount equal to the right ascension of the ascending node. This sets the correct location for the ascending node in the equatorial plane. The second transformation is about the new x-axis, which passes through the ascending node to properly orient the orbit plane at the correct inclination with respect to the equatorial plane. Mathematically, the transformation is accomplished by multiplying a 3x3 z-axis transformation matrix by a 3x3 x-axis transformation matrix, and finally by the unit vector 0, 0, 1. The resulting vector is the orbit normal vector, denoted O, and is of unit length. With unit vectors S and O derived with respect to the celestial inertial coordinate system, we can easily determine the angle between them. But since we are calculating the angle between the solar vector and a vector normal to the orbit, we'll need to subtract an angle of pi over 2 radians, or 90 degrees, from the result to obtain the angle between the solar vector and the orbit plane, which we will call the beta angle. First, we'll calculate an angle we'll call phi. The cosine of the angle phi is simply the dot product of the two unit vectors O and S that form this angle. When we substitute our expressions for O and S and multiply corresponding vector terms as prescribed in the dot product calculation, we arrive at our expression for cosine phi. And since beta is phi minus pi over 2 radians, we can form our expression for beta at the bottom of the chart. We see that beta is a function of only the ecliptic true solar longitude, the orbit inclination, the obliquity of the ecliptic, and the right ascension of the ascending node. For the purposes of this lesson, we're assuming here that the orbit inclination and the obliquity of the ecliptic are constant. The ecliptic true solar longitude varies with time, on the order of 0.986 degrees per day for Earth, and the orbit right ascension varies in accordance with the formula presented earlier in this lesson. Hence, we expect the beta angle to vary with time, and this will be dependent upon the orbit. Beta angle variation for an orbit is bounded to be within the range of plus or minus the sum of the obliquity of the ecliptic plus the magnitude of the inclination over the range of minus 90 degrees to plus 90 degrees. That doesn't mean that a particular orbit must experience the extremes, but rather it can be achieved if the orbit rate ascension and the position of the Sun south or north of the equator are conducive to producing that particular beta angle extreme. It should be noted there is a sign convention for beta angles. Beta angles where the Sun is north of the orbit plane are considered positive, and those where the Sun is south of the plane are considered negative. Here's a beta angle profile representative of an International Space Station orbit assuming perturbation only from the precession of the ascending node and movement of the Sun around the ecliptic plane. The short period variation is due to the orbit ascending node precession, and the long period variation is due to the Sun's motion. This is one of many possible beta angle profiles bounded by the sum of the obliquity of the ecliptic and the absolute value of the inclination. In this case, the orbit inclination is 51.6 degrees and the obliquity of the ecliptic is close to 23.5 degrees. So we see the orbit is bounded between about minus 75 and plus 75 degrees. So what does this mean for thermal engineers? As beta changes, there are two consequences of interest. The time the spacecraft spends in eclipse varies, and the intensity and direction of heating incident on spacecraft surfaces changes. Let's consider each of these effects. The sunlight is broadcast from the Sun radially outward into the solar system. A planet, or any object for that matter, that intercepts sunlight will leave shadowed region behind it. Regions behind the planet that fully obscure the sunlight lie within the umbral shadow. Regions where sunlight is only partially blocked lie within the penumbral shadow. The boundaries of the umbral and penumbral regions are determined by the line of sight vectors shown in the diagram. As seen from orbit, a spacecraft passing from sunlight to darkness spends some period of time in the penumbral shadow. For low Earth orbits, the time spent in the penumbra is very short compared to the orbit period. Additionally, the length of Earth's umbral shadow cone is much greater than Earth's diameter, extending many hundreds of thousands of miles into space, well past the orbit of the Moon. If the time spent in the penumbra is minimal, we can simplify the analysis by assuming the eclipse region is represented by a cylindrical shadow. The difference between the conical shadow and cylindrical shadow is shown in the diagram, where here the angle of the umbral shadow cone is exaggerated by a factor of approximately 4. To derive our expression, we'll consider a new coordinate system. In this system, the Sun is always in the coordinate system xy plane, and the orbit is inclined to this plane by the amount beta. If we look down onto the orbit plane, in this view, beta is 0 degrees. For this derivation, we'll consider only the circular orbit case. The vector pointing to the spacecraft is denoted as r, and the vector projection of r onto the coordinate system yz plane is denoted as r prime. The angle from the point between the planet and the Sun is denoted as theta. The planet radius is r sub e, and the spacecraft altitude is h. We seek an expression for the vector r prime, which, as we noted, is a projection of r onto the yz plane. We see from the diagram that whenever the magnitude of r prime is less than the planet radius r sub e, the spacecraft is in eclipse. We can express the spacecraft position in terms of the altitude, planet radius, the angle from orbit noon, and the beta angle. But for the circular orbit, this reduces to simply the sum of r sub e and h. When we project this vector onto the yz plane, we need only consider the j and k unit vector components of the vector. The magnitude of this projection is simply the square root of the sum of the squares of the j and k components. The condition of the onset of shadowing is when the magnitude of r prime is less than re. Rearranging the equation and isolating the terms with theta, we arrive at the expression at the bottom of the page. For a given planet radius, we see the shadowing as a function of only the beta angle and the circular orbit altitude. We now know the angle from orbit noon at which eclipse begins. By symmetry argument, it's also the angle from orbit noon at which an eclipse ends. Therefore, the total orbit angle in eclipse is simply 2 pi minus twice theta, as shown in the figure. And for circular orbits, the rate at which the spacecraft moves through its orbit is constant, so we can use this to determine the fraction of time a spacecraft in orbit spends in sunlight or eclipse. For the 408 kilometer 51.6 degree inclination circular orbit we considered before, we can clearly see that the time spent in eclipse or sunlight is a function of beta angle, and, dependent upon the circular orbit altitude, beta excursions above some value will result in an orbit in which a spacecraft is illuminated by the sun for the entire orbit. That is, there is no eclipse. For the 408 kilometer orbit considered here, betas above about 70 degrees in magnitude have no eclipse period. It is also observed that the time spent in eclipse is not too sensitive to lower beta angles. Again, depending on altitude, spacecraft in circular orbits spend a minimum of about 60% of their orbits in sunlight. Let's consider the geostationary orbit discussed in Part 1. As we saw, geostationary orbits have an orbit inclination of 0 degrees. That is, they lie in the Earth's equatorial plane. Since the inclination is 0, we see that the beta angles are limited to the range of about plus or minus 23.5 degrees. Because of the equatorial orbit, we expect to see only seasonal variation of beta and therefore eclipse periods. This gives rise to eclipse seasons for geostationary spacecraft. When we calculate the beta angle versus time for a geostationary spacecraft, we see the curve at the top of the page. Note that the long period variation is due to the seasonal variation of solar declination. And because the orbit lies in the equatorial plane, we do not see the short-term variation in change of the orbit normal vector with respect to the celestial coordinate system. When we calculate the percent of the orbit period in the Earth eclipse, we arrive at the curve at the bottom of the page. Note that much of the year is spent with the spacecraft experiencing no eclipse. But for 2 periods during each year, the spacecraft will experience some eclipse. Here's a closer look at one of the eclipse periods. The renderings at the top of the page depict the location of Earth's umbral shadow with respect to the orbit plane. Earlier, we calculated a representative beta angle versus time curve for the ISS orbit, shown at left. With beta versus time known, we can apply the equation we derived to show the time progression of the fraction of each orbit spent in sunlight. We see that much of the year, the time spent in sunlight does not vary appreciably from orbit to orbit. However, during times close to the winter and summer solstices, it's possible to achieve conditions in which the fraction of time in sunlight goes to 100%. The exact profile is dependent on the location of the right ascension of the ascending node at the beginning of the analysis, but this is just one representative example. Now we'll revisit the Sun-synchronous orbit from the perspective of beta angle. Recall that the Sun-synchronous orbit is beneficial for missions where having a consistent illumination condition is important, such as the case for Earth-observing missions. Such an orbit requires the orbit ascending node to move in the same direction as the progression of the Sun around the ecliptic plane. For a circular orbit, we saw that the rate of precession is a function of both altitude and inclination. And while a number of altitude and inclination combinations will achieve the desired result, Note in all cases the orbit inclination is required to be greater than 90 degrees. For our example, we'll consider the case where the orbit altitude is 705 kilometers and the inclination is 98.2 degrees. When we calculate the beta angle profile, we see that for this particular condition, the beta angle stays between about minus 15 degrees and minus 4 degrees, an 11-degree band. And recalling that the eclipse period is relatively insensitive to low beta angles, we see that the fraction of time spent in sunlight variation is on the order of 0.5%. The slight variation in beta angle in eclipse is due to the fact that the equatorial plane and ecliptic planes are not aligned, so that the ascending node precesses in the equatorial plane while the sun moves in the ecliptic plane. Additionally, the orbit is designed to precess in accordance with the average motion of the sun about the ecliptic, but due to Kepler's second law, the sun deviates from this average rate depending on Earth's distance from the sun. As a demonstration of just how well tuned the Sun-synchronous orbit is, consider the Sun-synchronous orbit analyzed in comparison to another orbit where the orbit inclination is changed from 98.2 degrees to 99 degrees, a seemingly small change. However, in comparing the beta angle versus time plot for both orbits, we see the orbit inclined 99 degrees shows considerable deviation in time. In this case, the beta angle span ranges from minus 14 degrees to plus 25 degrees. Comparatively, there is more variation in eclipse time for the 99-degree inclined orbit as compared to the true sun-synchronous orbit, but since the magnitude of the beta angle remains small, the variation of time spent in sunlight is only on the order of about 1.5%. In our definition of beta angle, we saw that the beta angle determines how sunlight falls onto the orbit plane. For negative beta angles, the sun was below the orbit plane. For positive beta angles, the sun was above the orbit plane. So for a spacecraft orbiting a planet in a fixed attitude, the environment experienced by a spacecraft surface such as a radiator or other component will change with beta angle. Consider the orbiting cube shown in the diagram. The green orientation represents a negative beta angle, and we see that sunlight impinges directly on surface 6, whereas for negative beta angle, surface 5 receives no direct solar flux. For positive beta angles, as shown in the red orientation, surface 5 now receives direct solar flux, whereas surface 6 does not. There are effects on other surfaces as well. Additionally, as the spacecraft passes over the planet below, the local illumination conditions will change, which affects the local overall heat balance. In the low beta case, the zenith-facing surface, that is the surface pointing away from the planet, experiences the full intensity of the direct sunlight at orbit noon. But at a beta angle of minus 75 degrees, very little sunlight is incident on that same surface. For a nadir-facing surface, that is the surface directly facing the planet, the sunlight reflected from the planet's surface, called albedo flux, is more intense than at higher beta angles. In the extreme, a spacecraft in a 90-degree beta orbits along the day-night line, a dramatic reduction in albedo flux as compared to the low beta case. Of course, the surface may be exposed to longer periods of solar flux as the magnitude of the beta angle increases. However, the change in angle with respect to the sun may reduce the magnitude of the solar flux. In Part 3, we considered the effect of orbit perturbations arising from Earth's oblateness. This led to our understanding of the precession of the orbit ascending node and the precession of the orbit periapsis. These perturbations can be exploited to create useful orbits such as the Sun-synchronous and the Molniya orbits. The effect of the perturbations on the beta angle and the consequences for spacecraft eclipse were discussed. In Part 4, we'll consider some advanced orbit concepts.